All right, so in this video, we're going to go over the D2 Tanabe-Sugano diagram and think about how many spin-allowed transitions there are for various complexes that this diagram is applicable to. So this diagram is called the D2 diagram, and so it's going to be valid for D2 octahedral complexes or also D8 tetrahedral complexes. Because the Tanabe-Sugano diagrams, the D10 minus n diagram is valid for tetrahedrals. Remember, there's this relationship between octahedral and tetrahedral symmetries. Okay, so first thing I always like to look at here is just remind us the different terms and axes. We have ligand field strength in units of B, the Rockoff parameter, measure of electron-electron repulsion. And we have the energy of the transition in units of B as well on the Y. And so we're looking at weak field ligands on the left side of this and strong field ligands on the right side of this. When we have zero ligands, field strength at all, we're free ion terms. Those are these singlet G's, triplet P's, singlet D's, triplet F states. But basically our ground state for any molecule that has octahedral symmetry for D2 or tetrahedral symmetry for D8 is going to be a triplet. It's telling us that here because of the 3 there. Let's just confirm that. Is that true? Well, for octahedral, we know that we split between the T2G and the EG in the molecular orbital diagram. And if we have D2 configuration in the ground state, both these electrons are going to be in the T2G, and by the 2s plus 1 rule, we have 2 spin ups here, and so we're going to get a spin of 3. That's why this is called a triplet. For the tetrahedral symmetry, remember it's inverted. We have the T2s, there's no inversion center, so we drop the G's and the E's. And again, if we, this time now we're D8, so we have to think about this here. So we populate 8 electrons. And so we're going to look like this. And again, we have 2 unpaired electrons. So we're going to get this same triplet ground state. So for octahedral, so this is write it in red here, this is octahedral. We're going to get the triplet T1G, that's the ground state. Okay, ground state. And for tetrahedral, we are TD. We just have to drop this G. So the G's are actually already dropped on most Tanabe-Sugano diagrams. So for tetrahedral, just copy what the diagram says. But remember, we're using the D2 diagram for, and that's applicable to D8, 10 minus 2 TD complexes. All right, so we have the ground states identified, and now to figure out the number of spin-allowed transitions, we just know our spin selection rules say that we have to keep the spin the same in order to have a spin-allowed transition that's going to have a high intensity. So in this case, we just look for our other triplets. So our lowest state here is going to be, let's say we're around this sort of ligand strength, would be going to a triplet T2. So a triplet T2G, we add a G for the octahedral. So our transitions would be triplet T1G to triplet T2G. I just took the T2 and added a G here for that first one. For tetrahedral, be very similar, but we just don't write the G's. And then we could go further on here and look at our next spin-allowed transition. We have a triplet T1 state up here. That's this line coming from the triplet P. Sometimes it's useful to look at the free ion term from which they're derived, just to guide your eyes a bit. And, you know, if we were the same molecule, technically we would be at the same energy here, or the same ligand field strength rather. So you'd want to draw this right at, you know, that same ligand field strength. I'm going to draw it offset just so you can see more clearly where oh, actually, no, this is fine. I had the wrong one there. So and we have to go up to right here. So that is going to be our next spin allowed transition. That's going to be higher in energy. So to occur at higher wave numbers or lower wavelength, we're talking about a UV vis spectrum. So again, it's going to go from the ground state. We're always going from the ground state, but now the excited state is another triplet T1G, okay, because there's T1 here. So that's this guy, and just to keep our color scheme, this was the triplet T2. For tetrahedral, so these are two different states, even though they have the same Mulliken symbols, okay? It can get confusing. They just happen to have the same symmetry. For tetrahedral, we just drop the G's, so it's going to be the same thing here, but just triplet T1 to triplet T1. All right, and then do we have any other ones? We do. We have a triplet A2. And so that one is coming down here. And so, you know, at this ligand field strength, this would actually be intermediate energy. But you could see that if we're at a higher ligand field strength, just because of the slope of this line, that would be the highest energy. So the positions of the peaks would switch depending upon where we are, what types of ligands we have. But regardless, we know that our third spin allowed transition going from triplet ground state to triplet excited state is going to be triplet T1G to triplet A2G. And so the same thing for our tetrahedral symmetry, we just drop the G's. So in all these cases, we expect three peaks, or three main peaks in the UV vis absorption spectrum for a D2 octahedral complex or a D8 tetrahedral complex. And that's how, you know, some information you can get qualitatively, we're not using this quantitatively here, for the Tanabe-Sugano diagram.